Okay, good morning, Physics 30s. So it should be Thursday, and if you have not gotten a cup of highlighters for your table, please grab that now. We'll just do a little bit of quick highlighting here. What we're doing today is we're going to talk about conductors and magnetic fields. So this has a lot of similarity to moving charges in magnetic fields. Just now, instead of the charges being a single loose charge, we're confining it to a conductor, like a wire. So we're actually talking about the current moving through the wire. So the outcomes for today are describe and explain quantitatively, so with numbers, the interaction between a magnetic field and a current carrying conductor. So that is, sorry, I lost my thing behind my recording box. That is green. Okay. Explain quantitatively, so with numbers, the effect of an external magnetic field on a current carrying conductor. So those are all green. What those outcomes actually consist of, what the types of questions that I'm going to ask you are going to, or that you need to indicate that you can do, are what comes next here under what you need to be able to do. So define current. So that's define. So that's yellow. Okay. Calculate any variable in current is equal to Q over T, which is a formula I introduced in the last unit. So I'm just going to assume that you know how to use that formula, this one here, because we've already done that one. Classify current, charge, and time as scalars. So that, so that's going to be green. Relate system international units. So current is in coulombs per second, which is also called amps. Use a hand rule to determine the direction of the induced magnetic field around a current carrying conductor, or the direction of charge motion, or the nature of the charge. So that induced magnetic field, actually that's something we're not going to talk about until Monday. That'll come up again. And calculate any variable in magnetic force is equal to current times length of the wire times the magnetic field. Okay, so those are your outcomes. And this is basically what's happening here. So the only thing that's changed in this situation, the only thing, is that now instead of it being just a single, like an electron, like before we would have had just electrons like going like that, or an electron moving that way. Now instead what we have is we have a current carrying conductor, so a wire that is placed in an external magnetic field. So we have that wire going around that way, where the short line represents the negative charge and the long line represents the positive charge. So with your hand rule, and this is the one limitation to the video, is you can't actually see me using my hand. So I'm going to write up what my thumb, my fingers, and my palm are doing here. So we have the force, the current, the magnetic field. They're all acting at right angles to each other, right? We've got the magnetic field. We drew the magnetic field lines in here. It's going this way, right? We've got the force drawn on there going upwards here. So there's the magnetic force drawn on there. And then we have the current, which is what I drew in red. So if we use our left-hand rule here, our thumb, my thumb, is going to point into the page. Okay, so into the page, because the current is going into the page. Think of that wire as kind of, it's drawn sort of angled there to indicate that it's sort of, we're looking at a three-dimensional sort of wire, so it's sitting flat, not flat on the page, but it's sitting kind of coming out of the page and going into the page. But the current itself here is going into the page. So that's my thumb. My fingers are going to point to the south pole, which is to the right of the page, right? So that's the south pole of the magnet, and that goes towards the right of the page. Okay, and so then what that indicates then is my palm is now facing to the top of the page, right? So that means that my magnetic force, so this is FM, my magnetic force is going up. So what that means is that wire is going to be pushed upward. So that wire itself will move, because all of the electrons inside it experience the same magnetic force. The entire wire moves upwards. And then just recall here, I just wanted to put in the formula here for current is charge over time, where I is current in amps, which has the unit A. Q is charge in coulombs, and T is time in seconds. Okay. So what this leads us to is being able to now use the third left-hand rule, which we learned Wednesday, to not only describe a moving charge in a magnetic field, but to describe a current carrying conductor that has moving charge in it. So then that leads us to the third left-hand rule for the force on negative charges moving through an external B. This should be for a negative current, not charges, negative current moving through an external magnetic field. So in this case, your fingers again are going to point towards the South Pole. Of the external magnetic field. Which is B. Your thumb indicates the flow, the direction of flow of electrons through the current carrying conductor, which is just a fancy description of wire. Okay, so that's wire. And your palm indicates the direction of the magnetic force on the wire. In other words, it shows which way the wire will move. When it's placed in that external magnetic field. And notice again, you use your right hand for conventional current or positive charge. And then just to remind you, dot means out of the page, and X means into the page. So take a second. It's going to seem very quick on here because I'm not going to pause the video. But try this example here. A current of electrons is running from left to right in a wire across your computer screen. If the computer screen generates a magnetic field pointing out at you, so out of the page, which way is the force acting on the wire? So you might just want to pause this video while you guys try this on your own. I'm just going to write up the answer. I'll kind of do a little bit of diagram here, but the answer is up. Okay, so it's going to move up, so basically to the top of the page is what I mean there. So if we have a current of electrons is running from left to right in a wire. So there's our electrons running from left to right. Okay, so that's my thumb is going to point from left to right. The computer screen generates a magnetic field that points out at me. So that's out of the page. So that's my magnetic field is coming out of the page. Okay, so this is my fingers. This is my thumb. And so I've always been writing that your fingers indicate point to the south pole of the external magnetic field. So that's the direction of the magnetic field. Remember that magnetic field points from north to south. So that's the other way of saying that, because we're not told north to south here, nor are we given an arrow. We're just said it comes out of the page. So then the force, if my thumb points to the right-hand side of the page, my fingers point back towards me, then my palm is pointing up. Right? So then I get a magnetic force going this way, going up. Okay, so we'll do a couple more examples using that. Then we'll look at a formula. So we want to determine the direction of first the magnetic force on the wire. So similar to the last question, but it looks a little bit differently. So I'm going to have, I want my thumb, my fingers, and then eventually my palm, right? Because palm is magnetic force, fingers is magnetic field, and thumb is the direction of the current, so E. Okay. So my thumb is pointing out of the page at me, right? So I point my thumb directly towards my face. It's pointing out of the page at me. My fingers now have to point towards the south pole, which is to the left-hand side of the page, and that makes the force upwards. Again, so there's a magnetic force going upwards. So it's a similar situation to the last question we just did. And notice, like, basically the charge and the direction of the magnetic field have kind of been reversed a little bit there. Okay, for this one we want to, for question B, we want to determine the current in the wire. So it's thumb is what we're looking for. So we'll be able to do fingers, which is magnetic field, and palm, which is magnetic force, and fingers is what we're looking for, and that's the direction of the current. So my fingers are going to point, my magnetic field is all the X's. So my fingers are going into the page, right? So that's X, so that's into the page. Back here, out of page. Okay, so my fingers go into the page. My palm points down because my force is down. And then my thumb, so now if I look at the way the wire's drawn on here, either the electrons are going to go to the right or to the left. And my thumb points to the right-hand side. So that's the direction the electrons are going, to the right of the page. Okay, so there's the hand rule, just like there was with the last, with moving charges and magnetic fields. And then there's also a formula. Okay, so, and this, again, it's a fairly straightforward, simple formula. The magnitude of the force on a current carrying conductor by the magnetic field is directly proportional to the current, the length of the wire, the length of the wire that's perpendicular to the field, and then the magnetic field itself. So that is magnetic force, Fm, equals current times length of the wire, times the perpendicular length of the wire, times the magnetic field. So we have Fm is magnetic force, and that's in newtons. We have I is current in amps. L, perpendicular, is the length of the wire that's 90 degrees to field. Okay, and that's in meters. And then B is the magnetic field in Teslas. And that's on your formula sheet. It's right around where the formula from last day is, Fm equals QVB. And there's also a second version of this if you have an angle, right? If the wire isn't perpendicular, if it goes in at an angle, you just want to find the perpendicular component of that. So it would be current times the perpendicular, or times sort of the length of the wire, times the magnetic field, times sine theta. So very, very similar. So just a couple simple examples. Determine the magnitude and direction. So we want to use the formula, and then we're going to use our hand rule of the force on a 2.4 amp current moving east through a 20 centimeter piece of wire inside a 4.4 Tesla field directed vertically up. I'll learn to speak one day. So current is 2.4 amps. The length of the wire, we need this in meters, so we're going to divide by 100 centimeters per meter. So that's 0.20 meters. And the magnetic field is 4.4 Teslas. So we'll deal with the magnitude of the force first. So Fm equals ILB, which is 2.4 amps for the current, 0.20 meters for the length of the wire, and then 4.4 Teslas for the field. Okay, and that gives us a magnetic force strength of 2.1 newtons. And then we need to use our left-hand rule to figure out the direction of the force. So we're looking to find palm. We know which way we can put our thumb and which way we can put our fingers. So remember, thumb is the current. The current is moving east. So the current goes east. Our fingers, the field is directed vertically up, so our fingers go straight up. Okay, which means my palm is facing into the page. Oh, vertically up, sorry. Let me fix that. Vertically up means it's coming out of the page at you. So the magnetic field is coming out of the page. So that's the magnetic field. My thumb points the direction of the current flow. My palm then is going to be, my palm is up, so then that's north, is what this is. Okay. You guys can stop and start this video as much as you need to. I'm just doing it continuously, so it takes a little less time to record. Okay, so how strong is the magnetic field if 2 meters of wire with a current of 10 amps is pushed downwards by a force of 12 newtons? So we have a force of 12 newtons. we have a length of wire of 2.0 meters, and we have a current in that wire of 10 amps. It's supposed to be a 10. We want to know the magnetic field. So Fm equals I times L times B. B is Fm divided by I times L. So that is going to be 12 newtons divided by 10 amps times 2 meters. So 12 divided by 20 is what that amounts to, so 0.60 Teslas. Okay, so and that's basically the sum total. We've now done all the formulas that we have to do in this unit. They can be combined, like especially the ones with moving charges, like what we did on Wednesday. But basically, that's it. Like this is in terms of what's actually on your unit exam. There's not a lot of material, just a lot of theory compared to the other stuff that we've done. Now, something else that we need to talk about when we talk about a current carrying conductor in a magnetic field is looking at the interaction of two current carrying conductors. And Ampere, who's the unit for amps is named after, he discovered that two current carrying conductors would exert magnetic forces on each other. And there's diagrams on page 607 that you can look at, but we're going to draw some of those diagrams on here. You can use the third left-hand rule then to determine whether the wires move together or move apart. Okay, so if we look at this, so let's say we have in our first example here, we're going to do two. So we'll have one example where we have a wire that has a current coming out of it. So that's electrons coming out of the page, and another wire that has electrons coming out of the page. According to if we go back to our first left-hand rule, which gives us the magnetic field that's induced around a current carrying conductor. So if we have an electron coming out of the page, right, our fingers, if we stick our thumb kind of coming out of the page and our fingers curl around so that we have a magnetic field like that. Except I'm going to draw this much bigger on here because I want it a little bit larger. So I have a magnetic field around that particular electron that's going clockwise. And then this one will be the same because it's also coming out of the page. So I have a magnetic field around that electron going clockwise. And if you think back to when we did the little diagram of the motor effect, or when I first introduced the magnetic force, I can think of this as being a bar magnet here, where this is the south pole and this is the north pole. I can do the same over here. I have a bar magnet here, where this is the north pole and this is the south pole. So then what we actually have happening here is an attraction, right? So these are going to be attracted to each other, right? You've got a magnetic force this way and a magnetic force this way. So the wires will be attracted to each other. Can look at a slightly different example. Let's keep the first charge the same. So we're going to have the first charge still coming out of the page, the electron. So that means we have a magnetic field going clockwise around that charge. But I'm going to make this other charge over here going into the page. So the electrons are going into the page. So now my thumb points into my page, which means my magnetic field is counterclockwise. So again, if I draw on a bar magnet, this one's going to look the same as it did in the top illustration. So south on top, north on the bottom. And this one's going to look the same as well. South on the top, north on the bottom. So now what I have here is I've got two south poles next to each other and two north poles next to each other. So the magnetic force is going to be away here. The magnetic force will be a repelling force. So the wires are repelled from each other. And that's it for this lesson. We just have one more lesson in this particular unit. Your assignment is in your booklet that you have. And I think it's page 163 to 169, numbers 1 to 18. I'm just going to double check that. looks like that's what it is. 163 to 169, numbers 1 to 18. And you can spend the rest of today working on that, and you're also going to have tomorrow, which is Friday, to work on both this assignment and anything from the assignment from Thursday that you didn't do or didn't get.